My presentation today is called Where Environmental Impact and Compliance Meet Design. And in design here, I have to admit to not be talking about design of buildings, but more design of industrial products, whether they aeroplanes or aircraft or washing machines. So my talk has got a few different bits. I'll give you a little bit of background, talk about some of the drivers out there in the wider industry. I want to talk about three specific challenges that our customers have. They're restricted and hazardous substances, critical materials, and what we might call eco-design. So that's a slightly different set of issues to the issues in the built environment, but not all that far off. I was going to give you a software demonstration. I've had a technical problem this morning, so I'll show you a few slides instead, unfortunately. And Chris has specifically asked me to talk about traceability of data, so I've got a little section on that as well. And I'll draw some conclusions. So that's lots of stuff. So who am I? I'm Professor of Mechanical Engineering, and I'm Managing Director of this company called Granta Design. And I'm Director of a couple of software consortia, but one is the EMIT Consortium, and that's the Environmental Materials Information Technology Consortium. And you can see that it's a bunch. In fact, that slide is a bit out of date. There's a few more members now, but they're largely aerospace companies. Emerson, of course, is well known. It makes everything else other than aerospace. All kinds of other stuff, consumer products and so on. But there's ARL is the Army Research Labs. NPL is the UK's version of NIST. It's a National Physical Laboratory, and that's the secretary of this consortium. This is a group which gets together to every 6 months to specify the software that we produce specifically for environmental issues. The other consortium that Chris mentioned, the Material Data Management Consortium, is actually meeting in Los Angeles this week. It's just the main reason that I'm here. It's concerned with software for material information management. So it's specified the core of product that we've built over the years, and we've added on to that a bunch of environmental stuff specified by this consortium. So this slide is not one that you can read, but here's just a few little bits of information. Granta Design specializes in materials information technology, in software and in data, and providing services for customers for implementing systems. We have a very large amount of reference data. I think the largest collection in the world of data for engineering industry, materials information for engineering industry. Very large proportion of that comes from other places. A small part of it we generate ourselves. We're a spin-out from University of Cambridge. Our investors, our owners are the university, ASM International, which is American Society of Materials, they're over in Cleveland, and our staff and so on. And we have these consortia, EMIT Consortium and Material Data Management Consortium, which are very important. So our customers principally are in aerospace, in medical devices, in materials producers, industrial equipment, and of course education. A third of our revenue comes from education market. There's about 1,000 universities around the world that use our software for teaching students about materials information. So that's mechanical engineers and material scientists principally, but also increasingly people working in civil engineering, architecture and product design. And we work with a number of partners, data partners. There's a set of data partners here. For example, MMPES is the Aerospace Bible for materials. Campus is a database of about 15,000 polymers that is produced by main polymer manufacturers and comes from Germany. And then we work with a number of software companies. So the producers of software systems for computer-aided design and for analysis, for finite element analysis and all those kinds of things, and we do integrations with them. So when we talk about materials information software, it's often a bit of a question of what that means, and it's materials information is one of the things which goes through all products and is one of the few things which is important from soup to nuts in a product. You know, there's many things about product development which don't start in conceptual phase of a product and don't end up in the use phase that you're not concerned about. But materials information and the geometry and the loads, they're things that are important from beginning to end. Materials information starts before product design in research. So there are many organizations that do materials testing. They pull bits of stuff apart or they set it alight or whatever. They need to get their arms around that data to do all sorts of data processing, scientific data processing, statistical analysis and so on, so that that information can then be used by the design people that are going to specify products or design buildings or whatever. So there's a whole part of this story which is about getting your arms around the material data in the first place, and a lot of that comes from test labs. Boeing, in the design of the 787, tested 30,000 coupons of bits of plastic. If you're going to do tests on 30,000 bits of plastic and generate complicated data from them all, you need to have some kind of a system to help you manage that information and to turn it into data that designers can use. So that's the sort of thing that we do. So designers need support tools, whether that's for analysis, you know, calculating the stresses or the lives of parts, or calculating the thermal response of the system, or you know, calculating the embodied energy, or doing an LCA, or working out what hazardous substances are in there. There's all kinds of things that designers need from materials information. Similarly, in production, when you make stuff, you need to know about the material that's coming in, the characteristics of it, and whether it meets the specifications and so on. And in service and end of life, there's again all sorts of issues when a 50-year-old airplane design has to be decommissioned. What do you do? Where are the nasty bits that you have to worry about? How do you disassemble it? What do we do with this part? What do we do with that part? So there are bits of materials information right across industry and various different kinds of software that meet those needs. So what are the drivers that we see in our business for environmental stewardship and environmental stuff? Well, first of all is regulatory compliance, and REACH, which I'll be talking about, has changed the landscape in regulatory compliance. I'll talk about that a bit more. Risk management, here's a picture of some pieces of tin with what are called tin whiskers growing. This happens if you have lead-free solder on your parts. You can get tin whiskers growing. That causes short circuits in circuit boards. It happens, has been the cause of a number of NASA satellites not getting where they need to get, not landing on Mars and stuff like that. It's a real problem because the aerospace companies that are buying circuit boards don't know whether their circuit boards are lead-free or not. Lead-free ones, which are prescribed by RoHS, have this problem. So how do aerospace OEMs know whether they've got environmentally friendly lead-free circuit boards, which might cause their airplanes to crash? That's a problem of risk management, and it's caused by the environmental regulation. And REACH brings a whole series of those sorts of problems into play. Brand image is important. This is again a REACH issue. These are two big supermarkets. They're stocking products with dangerous chemicals. Well, it's not that the products have dangerous chemicals. It's that the two companies concerned didn't have the information systems in place to answer the question from the NGO that asked them whether they contained a particular substance in the product. does that pair of sneakers have any DHP in the sole or not? We don't know. They were made in China. We can't say. Well, we will publish an article which says that you've not been able to tell us that. So there's a serious issue of companies being able to declare what's in their products, and if they can't, getting targeted by particular organisations. There's issues of marketing and market share, and customer requirements. There are security of supply issues. I'll talk about that a little bit more, but things like rare earths, conflict materials, substances which are difficult to get and which are critical. There are issues of cost. I thought I had a picture of Barbie here. I had a picture of Barbie's headquarters with a big poster on it, which was put up by Friends of the Earth, which said something or other. I can't remember, but what it was is that Barbie was being shipped in crates which were used timber which was not certified, and they put this 5-story high banner on the Friends of the Earth. Got up the building, put this 5-story high banner on Mattel's headquarters in California, and within a week Barbie had changed her source of supply of crates, and she was coming in nice sustainable wooden timber. So there are lots of these issues around. The principal issues that, and you can see some of the eco-labelling, environmental issues, restricted and hazardous substances, conflict materials. They are the 3 critical things which our customers tell us they have problems with, and so that's where we've been working. I'm going to talk about those 3 things a little bit today. So if we just look at restricted substances, it's interesting to just get a view of the product design process, which is shown here as a linear process, but is obviously not, involves lots of iteration. Starts off with some sort of design brief, ends up with manufacture and use of the product, and in between has some various phases of conceptual and detailed design. And if you take a view of this view of the world and look at where do people do life cycle assessments, then it happens at the end. This is what the conventional response to environmental issues in design is, to do life cycle assessment or report on compliance or generate your EPD or HPD at the end of design after you've finished, after you've built it. And you do your declaration, do your LCA. It's detailed and it's time consuming and it's difficult. And LCA requires all kinds of depth of information which is difficult to get about how the product is going to be used and how much fuel the recycling truck is going to use and that kind of thing. It's sort of minute detail. So traditional substance management systems are concerned with compliance management, checking their compliance or environmental impact also, we can put in there, at the start of production. So when you finish the design, here it is, check that it's compliant before we go into production. The people that do this are manufacturing and quality engineers, environmental health and safety people. The reference data that they need to use is the current legislation and the current set of banned substances. They need to check whether the part contains the current list of banned substances as it goes into production. There's an interesting example of this. One of our customers built a major system for the Airbus A380. That's the really big Airbus double-decker Airbus. And when they delivered this system, it was not compliant. It was made of a material which contained a banned substance. A substance, flame retardant, had been banned a couple of years before they shipped the product. So they started designing the product 6 years ago. In the middle of this, flame retardant, which is in their product, gets banned, and they continue to build a product not knowing that the product contained this particular flame retardant and not knowing that it had been banned. At the point when they delivered the product, which was a major system, very expensive, had cost millions and millions of dollars in R&D. At the point when they delivered the product, it was not compliant and it was illegal. That's a serious problem, and that can cause a company to go out of business. So this is a problem which is not necessarily about hugging trees. It's about companies staying in business because their product contains something that they don't know about. In the particular case, the company was able to get a special dispensation from the European Commission, had to go to European Parliament to get it, cost lots of lawyer fees, gave them enough time to go back and iterate their design and to change the product out, and the particular aircraft was late in delivery anyway, and they lived happily ever after, but it cost a lot of money and could easily have been a very sad story. So having non-compliant products is very serious. So you better check that it's compliant at that point. The tools that they use are compliance software, has fixed business rules. You can have so much of this, so much of that, and so on. And that's the way that it is done. Now, there are a number of reasons why that's not a very good model anymore. One is this, that when you look at the costs in products, this is the life cycle from conceptual design to use phase. And here is the percentage of life cycle costs in the money terms. And the blue line is the funds expended, and the red line's funds committed. So this is, we're not spending much money when we're doing design. We start to spend lots of money when we go into production and into service. That's when you're making stuff. On the other hand, you're committing resources in the design phase. And by the time you've got to the end of the demonstrated the part, you've committed about 85% of the life cycle costs. 85% you can't change anymore by the time that design exists. So it's not just the life cycle costs, of course, it's environmental impact, which is built in at the same time. So by the time you get to the end of the design, you've basically defined the environmental impact of your product. So you can't do anything about it other than change the design. Here's another thing that's happening. This is restricted substances legislation, and this is just the growth. Along the bottom is the number of substances which are banned in various sectors, starting earliest regulations from about 1976. And around the world, there's been an increasing amount of this stuff going on. In 2007, we had the REACH regulation, and that has changed the game significantly. So that by now there are thousands of substances which are banned in one place around the world or another. And so if you're building stuff in this global market, you better know which regulations apply in the market you're selling your stuff to. Of course, there's also individual companies that have their own requirements. Boeing has a list of stuff you're allowed to use, stuff you're allowed to not use. If you're building a submarine for the US Navy, there's certain things which can go inside the crew compartment and certain things which can't. And you better know that if you're designing a system to go inside an aircraft, inside a manned space capsule, inside a submarine. These are places where any off-gassing is really critical. It's important in buildings, makes the carpet smell funny. If you put it inside a space capsule, you kill the astronauts. So it's very important that you get these things sorted out. So individual companies have their lists of substances which are allowed to go in products as well. So there's a difficult environment that if you're trying to design things for global supply, lots of legislation, lots of company lists, and then comes along REACH, the registration, evaluation, authorization and restriction of chemical substances, came along in 2007. And I've said that it changed the game. Let me just read you something about Article 33. This is one little part of REACH, but it's an interesting part because it has a big impact. Any supplier of an article containing a substance meeting the criteria in Article 57 and identified in accordance with Article blah, 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 in concentration above 0.1% weight per weight, shall provide the recipient of the article with sufficient information available to the supplier to allow safe use of the article, including, as a minimum, the name of that substance. We unpack that. What it says is if you have more than 0.1% of a substance on this particular list, you have to be able to tell your end user about it. And that's where those supermarkets got stung by the NGOs. They weren't able to say whether they had more than 0.1% of particular substances in some of the products they were selling, and they therefore got blown all over the press as selling poisonous products. This is a really tough thing. Being able to say whether you've got 0.1% of a whole list of complicated chemicals in your product is a difficult thing to do. There are two parts to this. There's one part for OEMs, that's actually the second part, people that are selling to the public, and the other part is an obligation on suppliers, actors in a particular supply chain. And both have to be able to do that. In the case of the OEM, they have to be able to do it free of charge within 40 days of receipt of the request, 45 days. So any customer goes along to a supermarket and says, is there any DEHP in that pair of shoes? Walmart has to be able to say categorically whether there is or not. And that's a pretty challenging thing. It would be challenging if that was all there was. But if I tell you that the list of substances is going to change every 6 months and it's going to get longer and longer every 6 months, now think how challenging it is. If Walmart has a system which enables it to ask its supply chain about this set of substances, 50, 60, 70 substances, and then the list changes and a whole bunch more are added, within 45 days they've got to be able to tell the customer whether that substance is in the product. For every single product on the shelf. That's reach. So it's really interesting. And here's how it works. This is what we call the reach conveyor belt. So the reach conveyor belt has a bunch of steps. I apologize for the slides, but it has a bunch of steps, and they go from what's called the SIN list. The SIN list isn't even part of reach. It stands for substitute it now. And it's a list of about 400 substances produced by a group of NGOs, Friends of the Earth and World Wildlife Fund and so on. They've got together and they said, this is a list of stuff that we want banned. That's a perfectly reasonable thing to do. So the SIN list turns out to be a pretty good starting point. Most of the substances that have got into REACH have come from the SIN list. Now REACH has various stages, starting with Annex 15, SVHC dossiers. SVHC is a substance of very high concern. As soon as something gets specified as a substance of very high concern, you have to be able to declare whether you've got it or not. Right? Whether or not it's important, as soon as it's on that list, substance of very high concern list, you've got to be able to report whether you've got it. There's the candidate list, proposal for authorization. Authorization is interesting Euro speak. Authorization anywhere else would mean that you're allowed to use it. Authorization here means it's going to be banned. And it's called authorization because you've got to get a special authorization if you want to use it. Right? So once it gets to that point, it's going to be banned, and you've got to go and jump through a whole bunch of hoops if you've got some critical reason why you need to be able to use it in your product, and you get a temporary reprieve by paying a lot of money. And up here, the stuff is banned. Now, this has a time scale associated with it, and the whole time scale is about 6 or 7 years from one end to the other. And if we just see how REACH has been progressing, in June 2008, the SIN list had 267 substances, and the first 16 substances, SVHCs, all got into Annex 15, were all declared to be things on the watch list. In October 2008, 15 of them, of the 16, got onto the candidate list. That's the set of substances that you have to be able to declare, including this one, DEHP, which is a plasticizer. So this is my little case study here, DEHP. That was published in October 2008. In 2009, SIN list was upgraded, and 7 substances were proposed for banning, for authorization. There's a bit of other stuff on the other side which is not important, including DEHP. And so on. 2011, DHP was given a sunset date, and the total time is was 4 years after this, and that's about 7.5 years total. So what you can see is happening is that the number of SVHCs on the list is increasing through time. It's now, this slide is a bit out of date, it's now 60 or 70, and it's happening in kind of waves. So this sort of wave of materials is flowing through REACH, they start on the candidate list and then ultimately they're banned. And in the middle of that, manufacturers have got to be able to say whether they have them in their products or not. So this is a pretty challenging kind of environment. And under that environment, I showed you the top half of this slide before. The question is, how do you deal with that? What is it that we need to be able to do for product manufacturers to deal with this wave of stuff being banned? And it's important stuff. You know, it's stuff that makes up coatings and adhesives. It's stuff that makes up critical components of systems. Polymers and not metals in REACH, but all sorts of coatings and stuff like that. So what we need to be able to do in this world of real uncertainty about substances is try to minimize risk. What we don't want to do is go out of business. It would be nice if we could save the planet, but failing saving the planet, let's at least try to not go out of business. So what we need to do is think about risk, or what product manufacturers, aerospace companies, automotive companies, what they need to do is be thinking about their risk. And so the activities that we've got to do are compliance, of course, selection and substitution of materials and substances, design, and obsolescence management. How do you deal with the fact that a coating has just been banned and is going to go away in a couple of years' time? It's a critical coating on some part of the aircraft structure. What do you do about that? Well, you have to start a major R&D project. You have to work out what are the alternatives and whether they're going to be durable. You've got to qualify them and you've got to get them into service. That is a huge job for every single one of these parts and substances for a particular manufacturer. So you've got to embody environmental performance in the product in the first place. That's really the key. If you don't do that, then what you're at risk of doing is saying, okay, I can't use DHP anymore. What I'll do is I'll use this substitute. DBP is a good substitute for DHP. It's almost as good a plasticizer. And the manufacturer says it's okay. And then a year later you discover that it's also been banned because it actually has the same poisonous characteristics as DHP. It's just that it wasn't banned this year. So if you don't embody that environmental performance in the product in the first place, you're still using plasticized PVCs, you're in all likelihood you're going to be in trouble in the end. So you've got to have a forward view. What's coming down the pipeline in REACH, and how do we redesign our products so that they don't incorporate those things? And some of these products, you know, 747, the first 747 flew in about 1970. 747s are going to be flying till 2050. I mean, they have lifetimes which are almost as long as buildings, longer than commercial buildings. At least the design. Some of the particular products will be taken out of service, but the design runs for as long as a commercial building, almost as long as a residential building. So you need to have empowered materials experts and designers to do this stuff. You need to have future-looking data, tracking legislative trends, and you need strategic tools to help you in substitution, in design, obsolescence management. And if you're going to have those, if they're not within the native design environment of the people that you're expecting to use them, then they won't get used. So you need to somehow get the tools into the hands of the people that are going to be doing the job. So that's the set of challenges that we have in trying to produce software. So that's where we were before. This is the conventional response, LCA and compliance reporting just at the end of design. We think that you need to come in up here during the design phase where you're building an environmental impact into the product and have your substance reporting and design tools, your eco-design tools and so on provided to the designer. And that's really the key shift of emphasis away from compliance to risk assessment and eco-design. And that's the only way that we can see it being possible to handle this problem of reach. I'm going to move on. There's stuff about risk here, which I'm going to leave out, about the risk assessment cycle and what you want the tools to do. The product that we produce at Granta has several different components to it. It's based on a central database. Oops. Let's start here. Central database with reference information that's updated regularly. For example, information about legislation and substances and so on. Our customers need to be able to manage their own data because their particular materials they're using, the particular substances they're using and so on may not be the same as the standard reference information we've got. It's very important for them to be able to handle their specific data as well. So the reference data is important, but the customer in-house data is equally important. And then there's all sorts of information from suppliers, and here we get to the need for supplier declarations for suppliers to the equivalent of the EPDs and HPDs, but declarations about what is in the products that are being supplied, what are the chemicals, what are the materials, and so on. This gets used by three different groups. On the one hand, there's corporate groups of materials and process engineers who are doing risk assessments for the materials and products used by the company, risk mitigation, substitution, and so on. So they're the strategic thinkers inside the company that are trying to make the big picture decisions about material and process use. They need to know about the substances and materials being used. Designers within companies need to be able to incorporate best practice, best thinking in their eco-design. And finally, the product stewardship teams, the teams that are having to demonstrate compliance and so on, they need to be able to access this kind of data as well. So this information needs to be used across broad parts of companies for different purposes. And the tool that we've developed basically has this central database with a restricted substances data module, and then a series of different components for reporting, for doing materials substitution, for selecting materials, for risk assessment, for gathering supplier declarations, and so on. These are all things that companies need to use. And then integrated access from engineering systems such as computer-aided design systems, PLM systems, and so on. So that's the sort of structure of the thing. In the center is a restricted substances database, which contains information about materials and coatings, about manufacturing processes, the substances they contain, and legislation. So materials contain substances which are affected by legislation, but processes, manufacturing processes, might use solvents and cleaners or working fluids or refrigerants or whatever. They have restricted substances, and they're of course intermediates that are used in the manufacture of things which probably go away when the material is produced. Maybe there are trace amounts of those intermediates left on the material, and that can be important. You have something like Teflon, you know, PTFE, which is made from, we have on our frying pans. It's made from the most nasty stuff. If that nasty stuff ended up on your frying pan, that would be bad, very bad. So it's not that PTFE is bad, but the stuff that it's made from is very bad and could easily go away. So if you make Teflon PTFE coated frying pans, you better know that PFOA, which is one of the key ingredients, is likely to go away, and you may not be able to make your Teflon anymore. All right, so that's a problem that we've got, and that's because of the intermediate, not of the material itself. So we need to connect corporate MMP data with that information, be able to assess business risk, design out restricted substances, apply that within the engineering systems. Well, I can just show you a little bit of information. This is impossible to read, but this shows the contents of the database. A lot of this is reference data provided by Granta, information about materials and processes and restricted substances, legislation and coatings. We've got a team of people that puts this information together. And in a customer installation, then there is information about bought-in articles. That's all the 70% of the engine that you didn't make yourself. All the bolts and nuts and belts and control modules and gears and stuff you didn't make it. Rolls-Royce didn't make that stuff. 70% of the engine is bought-in articles. There's material and process specifications, there's in-house materials and in-house processes and so on. So you put all that information together and then you populate the system with supplier declarations. What are the suppliers? That essentially populates the bought-in articles. What does each article contain? Safety data sheets, customer lists, material and process specifications, and so on. This is impossible to read, particularly at this resolution, but here are some of the use cases. So one of the things is what we call predictive lists. Predictive list is something which predicts what's going to happen in reach in some years ahead. What's the best guess we can make as to where reach is going? If we can do that, we can help people say, well, you know, what are the things that we could be using in this design that are likely to not be banned in the future? That's pretty important. So that intelligence, understanding how reach works and trying to work out what are the best indicators of what is going to go away in future, that's very important. We do a lot of work on that. If you have that, then you can target your resources to mitigate various risks and get introduce substitution plans with suppliers and so on. Gain assurance of continuity of supply. So predictive lists and targeting of resources. Here is, this says Teamcenter. Teamcenter is the most popular PLM system, that's product lifecycle management system. It's equivalent of a BIM system for products. It's used widely by all the big manufacturers, and they store all of their corporate design data in there, all information about their designs. So it's very important for that system to be able to integrate with all this information. And so here's a little tool which I was going to demonstrate, but my computer is playing up. That's a Granta tool living inside Teamcenter, and it allows you to do all this chemical substitution stuff and materials assessment within Teamcenter. So now you're in your main corporate information system for product design, and you've got all that material and substance data in there as well. So you can run the reports. You can control material and process selection across the corporation. You can generate reports and dashboards and minimize risk, time to market. And here is another tool which is a web-based tool for analyzing bills of materials. So you've got a bill of materials for your building, generate a report on its LEED rating or something like that. It doesn't do that, but that's equivalent. So let me talk a little bit about critical materials and conflict materials. There was a report in New Scientist in about 2007. This says how many years left, and it's got all kinds of different materials, and it's making predictions about how many years left. And the concern was scarcity of materials. We're running out of stuff. Well, scarcity isn't really the problem. The real problem is political, and it's got to do with China banning rare earths, with conflict materials in Democratic Republic of Congo and other places. They're the things which are really driving scarcity of materials. It's not actually the stuff, the amount of it, abundance in the Earth's crust, which really matters, not at this point anyway. But whatever the perspective, the fact that you may not be able to get the neodymium you need to make rare earth magnets that you need to make generators for wind turbines or motors for electric vehicles, that's pretty serious. And you better know about it if you're making one of those products. If we look at the economic importance, this is an EU report, we've just plotted up the data, economic importance of materials, of elements, and supply risk. So up to the right are the things which are economically important, and up this way are the things which are at risk of supply. We can see that these are the set of materials which are a problem. Amongst them are rare earths, niobium, tungsten, graphite, indium, used for displays of computers, and some platinum group metals up here used for catalysts in cars, for example, platinum, and things like aluminum or other, you know, they're at low supply risk, high economic importance. Nickel up here, used for superalloys and so on. So these are the guys which are a problem. 96% of the supply of those materials comes from China or Brazil or Africa. So the things that we really, really depend on, these really critical materials, for computers and for high-tech devices and displays and all that kind of stuff, they come from places where there's supply risk. So that's the problem. So the critical material data module that we've built is one of those little Granta-only databases that we've built, contain these things: sourcing and geopolitical risk, abundance risks, monopoly of supply is important if there's only one or two suppliers or countries, environmental country risk similar, conflict material risk, you know, is it made in DRC, price volatility too. Things that are highly volatile in price cause risk to manufacturers. It's got data for 65 elements. And the important thing is the elements are linked to the materials that contain them. So that if you know what the material is, you can quickly say, well, this material is at risk or not at risk because of the stuff it contains. And that structure is important. So key use cases are assessing risk of supply, supply risk assessment for materials and for parts. I won't say any more about that, but I will talk about energy use and CO2 emissions, which I think is one of the things which is particularly interesting to you guys. You've all seen one of these pictures, right? This is the life cycle of a product, and the important thing is that there are, through all phases of the life cycle, through production, material production, through product manufacture, through product use and disposal, there are wastes, there's energy used, and so on. And life cycle assessment tries to add up all that stuff for the product. So we've focused particularly on energy consumption and CO2 emissions in environmental area. We've also got some stuff on water and so on. But the reason for choosing those particular things, first of all, is that they're big drivers of use phase costs. Second of all, they are things which manufacturers are universally trying to reduce energy consumption. And when you talk about some of the more obscure aspects of environmental impact, many companies are less interested in them. So our initial focus has been in particularly energy consumption and CO2 emissions. So here is the profile of a bunch of different products, and each one of these has got a little histogram which shows energy fraction in the life cycle of materials, manufacturing, transportation, and use phases. And what you see is that for civil aircraft, which burns fuel for 350, 60 days a year, and for 15 hours a day, 20 hours a day, the environmental impact is entirely in the use phase. And as I was saying to Chris before, it's not very interesting. If you want to design to minimize that environmental impact, what you have to do is make the engines more efficient and reduce the weight of the vehicle. And that's what those manufacturers have been doing forever. Boeing trying to reduce the weight of the vehicle, Rolls-Royce or GE or Pratt & Whitney trying to make the engines more efficient and lighter as well. So that's not interesting, they're already doing that. Family car is in much the same category. Lightweighting is the most important thing you can do. Embodied energy of materials is important, and particularly embodied energy of materials is important if you're interested in electric vehicles, because the embodied energy of lithium-ion batteries is huge. It takes a huge amount of energy to build lithium-ion battery, so that vehicle might appear to be environmentally friendly if you can run it off decarbonised electricity, which you can't. If you could, it might appear to be friendly, apart from the fact that the embodied energy in the battery is absolutely astronomical, and nobody ever talks about that. So that's a bit of a problem. So for a family car, electric vehicle, this material of manufacture is way up here. Refrigerator, so there's a typical appliance. Material is important, but again, use phase energy is important. The important thing is that your fridge keeps turning on and off every few minutes, every 10 minutes during the day. When it's on, it's using 450 watts of electricity, pumping refrigerant around the place and running fans and stuff like that. And that builds up to give a lot of energy in use. If we look at buildings, they're much more interesting. They're much more interesting. Here's a multi-story car park. Its energy is almost entirely energy of construction, you know, putting all that, building all that, making all that concrete. Very large amount of embodied energy in concrete. You don't heat a multi-story car park, so it doesn't use a little bit of lighting. Its use phase is dominated by material manufacture. A private house, depending on exactly how you look at it, the time period you're looking at over, the embodied energy in the materials and the amount of energy you're going to use in heating and cooling that house, depending on the time scale, are of similar orders of magnitude. So that makes it much more interesting. It makes it interesting to ask the question, is it better to put triple glazing on this window or not? Well, you're going to build a whole lot of embodied energy in, and you're going to reduce use phase energy. How does that balance come out? That's a much more interesting question, actually, than it is for an aircraft. And similarly, products like carpets and so on, it's the material that's most important. So we've developed a methodology for dealing with this stuff at Granta. It's a methodology which has two steps. One is to audit the product during the design phase and assess the amount of energy used in material manufacture, transport use, end of life. And then based on the outcome of that assessment, to focus on the parts that matter, on the use phases that matter. If it's on the phase of life that matters. So if it's use phase, then it will turn out that you need to reduce the mass, or you need to improve the thermal performance, or something like that. If it's the embodied material phase or the manufacturing phase, then there are design criteria which come with that as well. So start by doing an assessment during the design. Then when you've identified the key components which matter, you focus on those. And that's very different to coming along at the end of the process and doing an LCA and saying, yes, it was good, better than our competitors or not. That means right at the beginning, during the design, you're trying to assess what is the story about these things. So you have to use information that the designer has available, not that the LCA specialist has available. Or you have to make that LCA data available to the designer. These decisions are often material selection and substitution questions. And as I say, the key is to minimize the contribution of the dominant phase. So this is about optimization of particular parts to reduce their embodied energy, to reduce their mass, or whatever. But you have to know where you're targeting, and that's the key thing. So it's a two-step process. We implement that within the design environment. So here is a typical design environment in a company. They have this PLM system, like a BIM system. They have a CAD system, which is generating geometry. Engineering analysis systems, doing structural analysis and so on. Same kind of structure exists in the built environment, perhaps not quite as mature as in aerospace and automotive. What we do is we put this little database of all this good stuff that I've been talking about outside of the system, and then put our design for environment tools as plugins into these various packages. That means if a company uses 3 or 4 different CAD systems, which many of them do, they all can have exactly the same view of their design for environment information. And the bill of materials comes automatically out of the CAD system. So when you're doing your design, making your parts, you specify what each part is made of. We know the bill of materials, and our little tool knows what each of those materials contains in it, its embodied energy and so on, and it can generate a report telling you about the performance. We can do that in the PLM system or the BIM system. We can do the same thing in the analysis package. So it's just a simple architecture. Here's a set of these. These are 4 different CAD systems or 5 different CAD systems. This is the one I was going to demonstrate to you. It's on my computer, but it's broken. Some connection is broken. I don't know why. Here's that little Granta tool. NX is from Siemens. CATIA, which is important in aerospace. Autodesk Inventor. Autodesk Inventor, I believe, is used by quite a lot of people that make manufacturers of building products. So you could potentially have a little tool that the manufacturer of building products is using, designing his window, specifying materials, specifying manufacturing processes and so on, and it's then giving him an output. And the way this works is has a little dashboard and a bunch of reports. So you could easily have an output which was, or reasonably have an output which was an EPD output or HPD output direct out of the CAD package. That's the idea. So this has got outputs. This is various different possible outputs, embodied energy and CO2, restricted substances, water usage and so on, and reports in different formats. I was going to do a demo, which I won't. So I'm going to talk a little bit about data traceability. So I thought, so this was your special request, Chris and I, so I thought I'd talk about 2 things. First of all is reference data, traceability of reference data, and second of all, reach reporting. And these embody 2 important things, I think, about data traceability. So here's a bunch of data, which is quite interesting. This is the embodied energy, megajoules per kilogram in aluminum. And this is varying with time, so it's 1970 here, 2010 over there. And this is a whole bunch of data points which we've been able to collect from different sources. And here's a whole set of different sources that we can use to collect this kind of data. So one of the interesting things is you can see that the embodied energy of aluminum has reduced a bit over 20 years. Manufacturers managed to, it seems, the worst manufacturers managed to reduce their energy, embodied energy significantly. That's good. The other thing you see, which is quite interesting, is that up here where we are now, there's a factor of 3 from one end to the other in the embodied energy of aluminum. Now, if you ask the question, what piece of environmental information do you think we should be able to have a handle on better than anything else in the entire universe? It would be the embodied energy of aluminum. Because the aluminum industry is right in there trying to compete with the steel industry for car bodies and stuff like that. Embodied energy is right at the top of the list of important issues. And aluminum is so common, and yet there's a factor of 3 between the lowest and highest in the published literature. So if somebody asks you how precise is the environmental data in your LCA, just remember there's a factor of 3. There's a standard deviation of 30%, 40% in that data when you look at all possible sources. So data for environmental data is not precise. Even our most precise environmental data is very diffuse. And that's very important. We spend a lot of time checking this data, checking system boundaries that have been used, and where data is not available, we use models to estimate it. So the message is, I think the environmental data has inherently low precision, and you need to have systems which handle that uncertainty. Otherwise, you'll get the wrong answer. You need a lot of discipline in data collection and management to ensure that you've got good traceability. And to do that, you really need software systems which handle traceability. And that needs to be traceability of the source data, but also what you've done to the source data to put it in a common format with all the other source data, because you've done some kind of transformation, some sort of calculation to it to make it compatible with the other data that's available. So you need to store traceability of where it came from and what you've done to it. And that does take software systems when you're doing this across a wide range of things. Talk about reach reporting. Just like to draw a bit of a comparison between automotive industry and aerospace industry for reach reporting. The automotive industry has huge volumes of components, millions of components per year, and significant reuse of parts. Many parts in cars are reused from one manufacturer, one OEM to another OEM. So there's a lot of interest in the suppliers just declaring that information once and not having to declare it to every single OEM that they supply that stuff to. The automotive OEMs have a strong grip on their supply chain. They screw them down for price year upon year upon year. They can tell them to do stuff because if you don't do stuff, I'm going to stop buying 1 million parts a year from you. And they really have a strong grip. They've, as a consequence, been able to generate a system called IMDS, International Material Data System, over about 10 or 12 years, where all the suppliers declare what's in the parts that they make. So automotive, big success for automotive industry. And it's because of this set of characteristics that they've been able to do that. Not everybody can do this. Not everybody can make an IMDS. Aerospace system, small volumes of components. We don't make many airplanes every year, 1,000 maybe. They're all different. Parts don't get reused from one to another. Because there's so few parts, the aerospace industry has weak grip on its supply chain. It's not able to screw them down for price, and it's not able to get them to do stuff. And the consequence of that is the aerospace industry has taken individual approaches. All the different companies are taking their own individual approach to getting their suppliers to do reach declarations. There is no IMDS, central IMDS for aerospace, and not really any prospect of it happening either. So these are two industries that have very, very different dynamics, and very different dynamics, again, from the built environment industry. So the declaration process is interesting. Here's the customer, here's the manufacturer, and here's the supply chain. And the process that's happening is that substances are added to that candidate list, and now the manufacturer has to be able to declare. And so he, in a great panic, goes and requests from up, actually it's kind of inverted, up the supply chain to all of those suppliers, what is in, does your component contain this substance? And ideally that reporting goes on and everybody reports back, and now the OEM knows whether the particular substance is in the parts that he's buying. The only problem is that he's got 2 million parts, and this supply chain has got just millions and millions, tens, hundreds of millions of different organizations involved in it. So the idea that you add a substance to a candidate list and then suddenly within 45 days, right, this has to happen in 45 days, because if it doesn't, you get targeted by the OEM, by the NGO that is asking you whether you've got DHP in the flip-flops you're selling. All right, so this has got to happen in 45 days, and there's tens of millions of companies involved in this supply chain, all the different parts that you make. This is an utter nightmare. So the problem with this is the reporting time frame is very short, 45 days, immediate for Article 33.1, 45 days for Article 33.2 of REACH. It's very slow to gather the data. Supply chains are complex and global. There's no legal obligation for American suppliers to actually declare to European companies. You don't have to. European companies do have a legal obligation to declare, but Chinese ones don't. So you don't have a legal way of getting to them. The obligations apply to spare parts, and some spare parts for airplanes have been stockpiled for 30 years because we don't make them anymore. So that's interesting. There's no supplier to get declaration data from. We don't know what they're made of. That's an interesting problem. Many suppliers are unwilling or unable to provide the declarations at substance level, particularly for industries that are new to reporting and not automotive. So the harsh reality in this is that the norm in REACH is going to be absence of data. you're not going to have the supplier declaration data that you need. That's just life. There's no ideal end state which says that everybody's going to have all the data for all of the products. We have to have systems which can deal with it without having the data. So how do you do that? So this is the ideal situation. So here is a database. Here's a user material record. I've called it PVC Blue. And PVC Blue contains a bunch of substances. And here's our substance list in the database. Lots of different substances. These ones all start with A. And we know that PVC Blue is connected to a bunch of those, and we've got information about what it contains. So the ideal situation, and you populate these links by supplier declarations. You ask your suppliers, does PVC Blue contain any of this stuff? And he says yes or no, and so you've got that information by asking your supplier. And so when you come to analyze your bill of materials over here, here's your bill of materials. Component number 123 is mass of 20 kilograms, 40 pounds, 45 pounds. And it's made of material PVC Blue. And so we can follow the links because we know that this link says PVC Blue contains, 0.5% of DHP. We can say 20 kilograms, 0.5% of that is DHP. Okay, we know how much DHP there is in that and go through the whole bill of materials that way. So that's what you would ideally do. The problem is, of course, so there's your REACH compliance report, no worries. The problem is that you don't have the declaration data. So what do? You have to give the declaration straight away within 45 days if you're selling to the public. What we do is we set up a parallel universe. MU stands for material universe. This is our parallel universe of materials. This is the user's material here. This is the material universe which contains what we call generic materials, about 4,000 generic materials that are used, that each represent the 100 or so thousand materials that are available to designers. And it has something which says, a field which says it may contain particular substances. So flexible PVC may contain DEHP and may contain DBP and may contain DOP, all the things that it may contain and the percentages which are likely. And we can find that out because you can look around the web, you can ask suppliers, you can go on the ECHA website, European website, and you can find out which materials are likely to contain which substances and in what percentages. So we know that. We know the worst case. Flexible PVC at worst case may contain 20% DHP and 25% DOP and so on. So we can populate those links ourselves. We call that where used data. We can, and when the list changes, a new substance comes along, we can add the link to all the materials that it used in along with that information. We call this we make what we call as a fallback link between these two records. And so what happens is when we're analyzing the bill of materials, we say, okay, it's made of material PVC Blue. Guess what? No supplier declaration. Okay, what's the fallback link? Flexible PVC. Flexible PVC, we know it might contain 20% DBP. Terrific. Down here we can say, guess what? Your part might contain 20% of however many kilograms of DHP. And that is terrific because when you get this report, a day after the new, a few days after the new material has been added, new substance has been added to the list, we've populated that where used data link. You can immediately say whether it's likely to be in your bill of materials or not. And you never need to go back to ask the supplier to get that level of information. So what comes back is, instead of these 2 million parts that you have to go ask for supplier declarations for every time the list changes, all you do is once get information about what the materials they're made of, and from then on, every time the SVHC list changes, that information is reflected in the reference data, and it says there's 20 parts in your inventory which might be affected by this change to the REACH list. You better go and ask the suppliers whether they've put any DXP in that, because if there is, you've got a problem you need to deal with. So this is a risk assessment tool. Instead of having to go to manufacturers of your 2 million parts and all of those supply chain actors in multiple declarations, we go once, we ask them what materials the stuff is made of. We use these fallback links, and that gives an ability to assess the likelihood of something containing the banned substance. And we've applied for patent on that. So the benefits of this is that the supplier declares the material contents of the part, not the substance content. You declare it as flexible PVC, not all the CAS numbers and ingredients. You don't have to do that, that's done for you. The supplier makes a declaration once, not repeatedly. Just have to say once what are the materials, not multiple times whether particular substances are in there. It's a risk assessment. It's not a precise compliance calculation. It doesn't tell you whether the product is compliant. It just tells you whether it's likely to have a problem. You've got to go another step to get that compliance information. You only need detailed chemical declarations for parts that are likely to be a compliance risk. And you can focus your effort on those particular parts. Go and talk to those manufacturers. So you can focus your resources on reporting, compliance, on substitution for a small number of risky components. And that's the key. The key is to deal with this massive information, get you focused on the things that really matter rather than the 2 million supplier declarations. The return on investment is substantial because you save all that organisation that needs to go asking suppliers for stuff all the time, and suppliers don't have to keep providing information, so everybody wins from doing that material declaration once instead of substance declarations. So here's my summary. These are the things we focus on: conflict materials, restricted substances, energy use and emissions. We really think it's important to get this right during design and not wait till compliance at the end. There's a systematic methodology for doing all this stuff, and most importantly, we need to have the tools inside the engineering environment, the design environment, inside the building information system, inside Revit, inside your building CAD system. That's where the action needs to take place. Otherwise, it won't never be used. Maximize the benefit and minimize risk and costs by considering eco-design early. Materials and processes and product data are the foundation of eco-design and substance management. Access to that data needs to be integrated with the designer's normal workflow to enable rapid iteration in design, refinement, optimization, and risk reduction. And key tools for this are auditing of products, risk assessment, material and process selection, optimal material process selection, material substitution, and obsolescence management. They're the things that those customers need to do. So to have a systematic approach to sustainable design and risk management. Okay. Not much about buildings, but I hope there were a few little nuggets that were interesting.